Hello and welcome to 10-Minute Physics. Today, in 10 minutes or less, we'd like to take a look at Newton's third law, make sure we understand some of the nuances, some of the difficulties, and really make sure you can wrap your head around this law because it's very important. Before we do, let's just recap very quickly Newton's first law and second law. With Newton's first law, we are concerned about what happens when the forces are balanced. When the forces are balanced, you have two results. There is going to be no acceleration, but you have two things that can happen. That object is either going to stay at rest or it's going to stay in motion, and it's going to have the same speed and direction. With Newton's second law, we are talking about when the forces are unbalanced. When there is no balance of forces, there's going to be a net force. This net force, this comes from the equation F net equals ma, and we know there will be an acceleration because there is a net force. A net force means there is an acceleration. And we talked about how the acceleration is going to be directly proportional to the net force, as we see here, and it's inversely proportional to the mass of the object. Okay, very quick, very straightforward review. All right, let's get on. This is probably the definition that you have seen and you regurgitate, and it really means nothing. This is the absolute worst definition you could use, and I'm going to tell you right now, stop. Do not use this definition. It is going to cause you problems. It is going to lead to some difficulties. Okay, I will draw a little diagram. Let's say we've got a child on a swing. Okay, there's the chain and there's the seat. Okay, what do we have acting on here? What are the forces acting here? Well, most students will say we have a weight force which is acting down, and then we'll say, oh well, we've got there's a normal force which is acting up. It's the contact force between the chair and the person. The chair is pushing up on the child, and then you'll say something like there is an equal and opposite reaction force. And then you'll say, yeah, these forces are balanced. This is Newton's third law pair. Forces are balanced. Every action has an equal and opposite reaction. Every force has an equal and opposite force. You know what? Like I've seen definitions where they don't even use force and they just say every action is an equal and opposite reaction. Absolute poppycock is what this is. This has nothing to do with Newton's third law. Okay, this is the real definition of Newton's third law. This is the way I would recommend that you think of it. It's the force exerted by object A on object B. It's equal in magnitude and opposite in direction to the force exerted by object B on object A. Okay, so if I've got two objects in contact with one another, okay, maybe there is some sort of external force, okay, and that object A is pushing on object B. Okay, this is object A, this is object B. There will be object B pushing back on object A. So maybe object B is the floor, maybe object A is this box. And this box is moving along, it's being shoved along. There's a force that's being exerted, okay? This force is moving, okay? And so what's going to happen is the force exerted by A on B might be the force that you're supplying, that you're moving it along with, okay? And the force of object B back on object A might be the friction. And so if the force with which you're moving object A along, if it's equal to the friction, if these forces are in fact equal, then the net force is equal to 0, and this object will move along at a constant velocity. Okay? And it will not be accelerating. So when it's moving, it will have constant motion. Okay, you could look at these forces here. We have a box on top of the floor, and you could talk about the force of the object acting on B, and there will be a restoring force of B acting up on A. And again, no net force, and therefore this object is not accelerating vertically. It's going to stay at rest, and it's not going to sink into the table. It's not going to sink into the surface. It's not going to float and rise up. It's not going to be pushed upwards. Okay? If you set down a heavy book in a beanbag chair, then you might find that this force is a lot greater than the restoring force of that material, and so the net force would not be 0, and it will slowly sink in. We can express this third law in a mathematical form, which I think is far more, well, it's definitely shorter to write down, but easier to understand. You're going to have F, the force of A acting on B is equal to negative the force of B acting on A. Now, this is maybe a little more A-level than GCSE. I want to go back to this child sitting on the swing. Okay. Now, what were we saying before? You know, we'd said in the previous page that the normal force was equal to the weight. Okay. But in order to have a Newton third law pair, they must be the same type of force. Ask yourself, what is weight? It has to do with gravity. It's the gravitational pull, okay? Whereas the normal force is a reaction force, is a contact force. These are not the same forces. This is not how we look at the situation, okay? And they must involve the same two objects. Are we involving the same two objects? How do you describe the normal force? Well, it's the force of the seat on the child. Okay, and what about the weight? What's the weight? Well, the weight is the force of it's the pull of gravity on the child. Pull of gravity on the child. In other words, it's actually the force of the earth on the child. So if you want to make Newton's, there's actually two Newton's third law pairs. Okay, the first one is what we've got from the normal force. Okay, that's the force of the seat on the child, whereas the force going down, that child is exerting a force, the force of the child on the seat. That's a Newton third law pair. This is the contact pairs. Okay, the other thing you can have, if you look at the weight of the child, that is the force of the earth acting on the child, pulling it down. When you jump up, you land. Okay, when you trip, you fall into, because the earth is pulling you down. You are also exerting a gravitational pull on the earth. You are pulling the earth up into you. Okay, and so that weight is equal and opposite. It's the same gravitational force. Okay, that I don't know why I've written an equal sign there, but it's the same in magnitude as you, that child, exerting a force on the earth. This here is a gravitational or force at a distance pair. Okay, it's the same two objects. Up here, it was the same two objects. Here, all right, when you just look at this and you go with that really horrible definition of every force has an equal and opposite reaction force, you say, oh, those two forces are equal. But as we had said, that's actually the force of the seat on the child, and this going down is the force of the earth on the child. There's three separate entities and objects involved there, and that can't be for a Newton third law pair. So make sure you understand this. Make sure you get what's going on. Needs to be the same type of force. So you know, a contact force is not going to be the same as an electric force, not going to be the same as a gravitational force or magnetic force. Okay, there's different types of contact forces. Yes, there's friction and tension and all that sort of thing, but you have to take a look at the same type. Okay, the other thing is on the same two objects. If you've not got them on the same two objects, then you've not looked at this correctly, and that can lead to some problems. This is a more correct analysis of what's going on in this situation. Yes, it is true, all four of those values would probably be the same, but in terms of Newton third law pairs, need to be acting on the same objects. Okay, so when we go back to this mathematical formula here, this is what it's showing you. It's showing you two objects. Yeah, A acting on B, B acting on A. And it's the same type of force. This is a much more complete definition of Newton's third law, and I highly recommend that this is the way you learn. And you can just simplify it by looking at this mathematical version of that equation. This here is a horrible way to summarize third law, and I ask you to denounce and reject this definition. It causes way more problems than it does good. It is not a good simplification. And actually, this version and this equation, you will see, actually leads to a better understanding of conservation of momentum. So please think of this as being your third law of definition. So we've just gone through some of the common misconceptions of Newton's third law, specifically the pairs. I hope that works for you. If you enjoyed this video, please comment, rate, share, like the video, and if you've got any questions and other things you want to talk about, then please drop me a line. That's all for now. Thank you very much. We'll see you next time on 10-Minute Physics.